My name is Andrew Schran. I'm a platform software engineering intern, and I'm pleased to introduce today Marty Connor, Michael Brown, and Peter Anvin, three people who I've had the pleasure of working with for the past couple of weeks. They created gPXE, which is the state-of-the-art in open source network booting. And today they brought a bunch of awesome demos, as you can see, to show us, and some stories of their experiences as Google Summer of Code mentors. So thank you very much for coming to speak for us.
All right. I am Marty Connor, etherboot project leader. This is Michael Brown. Michael is our lead developer. And this is HPA. Most people already know who he is now. But this is H. Peter Anvin. And what do you call yourself these days?
I'm here as the creator of the SYSLINUX project, which includes the Pixie Linux network booting stack. Other than that, I'm a Linux kernel engineer at a company called RPath.
Yep. So we want to introduce gPXE. How many folks here have already heard of gPXE? Cool. All the people in the front of the room. All right. What are you people in the back of the room doing here? All right. For those who have not heard of gPXE, how many people have heard of etherboot? Wow, OK, so more people have heard of etherboot. OK, I want to introduce the creator of etherboot, who happens to work at Google, Marcus Gutschka, in 1995, was interested in network booting because he didn't have enough money to boot 2 computers. But he figured that if he rewired his power supply and then did this little hack with network booting, he'd be able to boot 2 computers for the price of 1. Is that fair to say, Marty?
That's a pretty good summary, yes.
There you go. So therein started the long odyssey from 1995 to the present of the etherboot project. Marcus was the first project leader, and his big motivation for porting etherboot was that he didn't want to write his network drivers in assembly language. He wanted to write them in C. So he created the capability of writing C network drivers, which was a big deal. All right, fast forward a little bit. A couple years later, a fellow named Ken Yap became project leader. And Ken was project leader for like 10 years. And under his leadership, etherboot grew and grew and grew in popularity. Now, how many people know about Pixie? If I said Pixie, how many people would just say, oh, I know what that is? OK. For those that don't know, when you start up your computer and it says boot from LAN, that's Pixie. It is the part of the BIOS that it's a BIOS expansion component that allows you to boot from LAN. Where's Peter? OK. I should tell you this. There are 3 of us here today. The 4th person who couldn't make it is Don Becker, who wrote most of the Linux network drivers up through the year 2000. Don had to go back to Maryland. He couldn't be with us. He was with us at Linux World. But what you do have here is probably several of the people in the world who know the most about network booting. It's a peculiarly small community of people who are really interested in this. But for some of us, it's the coolest thing we ever saw. And we've got some demos to show you. Now, a little background. What year was Pixie Linux?
Pixie Linux. Is this
Yeah,
thing going?
Yeah. It's on.
OK. Yeah, so Pixie Linux was came out in, was it 1999?
Yep.
When Chris DiBona, who is also now at Google, dropped the server in my lap and says, hey, make this thing network boot, which I had foolishly enough to express interest in doing. I also grabbed a hold of this specification called the Intel pre-execution environment specification, which was an attempt at taking this hideous situation that we were in, that every OS times every NIC needed a different hardware component, a aftermarket ROM, in order to be able to netboot. Unfortunately, the PXE specification is, to say it's awful would be like flaming awfulness. It
has certain deficiencies.
It's suboptimal.
Suboptimal. Like really, really suboptimal. Like assigning the same opcode for 2 operations awful. Yeah, so it's unimplementable.
It's actually unimplementable for several other reasons too. But that on top of that was that the early implementations were just incredibly buggy. And when I say incredibly buggy, it was, there was this long list of errata that like, oh, in this version 0.99J or whatever it was, we fixed the, we fixed the bug that we send packets to the wrong gateway.
Yeah, it was pretty amazingly broken.
Yeah.
But it was the best that we had.
In particular, having when it comes to booting, the sad situation is that having even an awful standard is better than having no standard at all. And so one of the limitations of that PXE specification imposed was that the boot program couldn't be more than 32 kilobytes long. This turned out to no one actually implemented this limit, but at this point, I had seen just about everything before I even started. So I was like, okay, I'm gonna play really, this really tight to my chest. I had written a small bootloader called SYSLINUX that was intended to be used on floppies and therefore was small already. So it seemed like a good point to start, and it had a pretty decent feature set. People liked it, so I'm like, okay, well, rather than starting over and doing it all from scratch, I might as well just start it from there. And, so that's how PixieLinux came to be, and it's gotten rather popular.
Yeah, like pretty much it's what everybody uses to boot, to network boot on Linux. Okay, this is supposed to be interactive. Please. If there's anything you want to know, if there's anything that's unclear, if you have any question at any level of technical specificity, ask it. You pretty much have like somewhere between Marcus and Peter and Michael and myself. We probably can answer it. How many of you guys are from the BIOS group? We're the BIOS guys. Okay, so you're comfortable with expansion ROMs, evil expansion ROMs that do all kinds of like really naughty stuff.
Evil.
Evil. All right, so yeah, so don't, do speak up. All right, let me tell you about the timeline here. The etherboot project started in 1994, 95 or so. 1.0 came out in like...
I think it was August 95.
Yeah, it was like August 95. We were first. Pixie was second. We were very proud that we were first. And the etherboot project back then sort of did its own thing. It worked something like this. We would take a kernel, and we would run it through, we would wrap it. We would wrap it using something called make NBI. What's NBI? Network boot image. There you go. This is a really cool idea because what it does is it allows etherboot's network loader to be incredibly simple. So the basic pattern is like this. Etherboot does a DHCP request, gets back the usual stuff plus a file name. The file name is important. The file name is used by tftp to load the NBI file, and also the NBI would take a kernel and an initrd back then, and away you go. Pixie, where'd Peter go? Pixie had a different approach. The Pixie folks didn't define it that way. You wanna do the Pixie side? Or you want me to? I can go real fast.
You go
Okay,
for it.
I'll go real fast. Okay,
I'll flame you when you get it wrong.
flame me when I get it wrong. It's, you know, it's really fun to get flamed by like the x86 maintainer of the kernel, you know, because, you know, he wouldn't bother unless it was like worthwhile to flame. Okay, so on the Pixie side, Pixie was theoretically supposed to fit in 32K, but nobody paid any attention. What Pixie did was it loaded something called a second stage loader, which was NBP, which was called a network boot program, or NBP. So what happened was Pixie. Okay, so how many people know how option ROMs work in the BIOS? Couple? All right, let me tell you a little story about the BIOS. Okay, from time immemorial, the BIOS has started up and peered at a certain space in memory, looking for friends. It's a lonely BIOS. It's looking for people to join it. Those things are option ROMs. You'll notice when your computer starts up and you have an Adaptec SCSI card and you've got some fancy VGA card, and you'll see these things going by announcing the copyrights of the companies, and sometimes saying hit Control S or hit Control A or hit Control. Those are option ROMs. Typically, they're either living in the BIOS on the flash on the motherboard, or they're living on an Ethernet card or on a SCSI card. We implemented one. Long story short, there's a way to do them. They start with 55AA. They land on even boundaries in memory. And if you, yeah, sort of. And if you put your ROM on a card in the right format, it will get loaded. So that's essentially what we did. All right, how bad did I do?
Good enough.
Good enough, okay. All right. So etherboot and Pixie could both be put on a little ROM chip on an Ethernet card. When etherboot started up, it did its DHCP, it got the file name, it TFTP'd it into memory, and it executed. Done. Finito. Bye. Okay, Pixie, on the other hand, had another idea. What they did was they did DHCP. So far, so good. They got the file name. All right, now here's where it's different. The file name was not assumed to be something that was immediately what you wanted. It was a thing to get you what you wanted. So it was a second stage bootloader. So then it loaded the
NBP.
The NBP, thank you. NBP, or the second stage loader, which then was smart enough to load what you really wanted. In this case, you wanted a kernel. Let's say you wanted a kernel and a init ramfs, and the NBP would do the loading. Okay, the etherboot method of doing this saved a step. It was, but at the cost of having to wrap your kernel and your knitRD. Some people like this. Some people still use this to this day. The problem is that Intel came out in 97 with the wired for management, or WFM. WFM.
As opposed to WTF.
WFM was wired for management, and in an appendix in the Intel wired for management specification was the PXE, or pre-boot execution environment. The pre-boot execution environment defined the Pixie way of network booting. Now, we in the etherboot project had been merrily chugging along, booting all sorts of things. We'd been booting supercomputer clusters. We'd been booting, LTSP things. We'd been very happy about life. But it became very clear that the industry as a whole was moving toward this. All right, I got to step over here to my friend Marcus. All right, Marcus, do I need to get real technical real fast? Are we okay? All right, okay, I just want to make sure. He's my technical audience here because, I don't want to bore you with this history stuff, but it's important you understand why we created the first open source Pixie. We created it because as much as we loved etherboot, and some of us loved it a lot, we decided that since the entire industry had gone this way, that if we didn't implement this as an open source thing, we were going to become less and less interesting over time.
In the meantime, an almost daily question on the SYSLINUX mailing list and IRC channel is, what do I do with this system that has a broken PXE stack and ROM? Because this was more than an occasional question, shall we say.
So what we did was we implemented PXE in first in etherboot. So what we did here was we gave the option of people, instead of directly loading NBI files, of actually loading Pixie bootloaders. So we actually kind of, as a first step, this was kind of when I wandered into etherboot in about 1999 with all this crazy talk. This crazy talk of, like, implementing Pixie. And it's about as popular as, like, talking callbacks to a core boot hacker. You know what I'm saying? So how many core boot hackers are there? I know there we go. I knew he was out there. All right. Core boot is a replacement for the BIOS, for the normal PC BIOS, for those who aren't aren't aware. And there's a certain amount of, shall we say, disagreement about the value of core boot in the modern booting thing. But we're coming around. We're coming around. Don't rush the audience. Okay. All right. All right. So 1999, I joined the etherboot project, started writing device drivers, talking this crazy talk. Then then about 2000, I created a website that sort of disrupted the normal flow of the world, called romomatic.net. Up until then, in order to use etherboot, what you had to do is to download a tarball, cd to the source directory, type make, and seemed simple enough. Well, it wasn't simple enough. So what I did is I created a website, romomatic.net. Matter of fact, just for fun, let us go to romomatic.net, and I'll show you, pardon the Fedora Core 6. All right. OK. What romomatic.net is a boot ROM vending machine. I used to sit on the etherboot users mailing list all day long, and people would say, I want to use etherboot, but I'm on a Windows machine. I can't download it. What's this make thing? So basically, I wrote my first PHP program. I'm so ashamed. It looks like Lisp. I mean, it's like really, really ugly PHP. I don't even want to talk about it. But what it did was it suddenly allowed anybody that wanted to build a boot ROM. And for the first 2 million boot ROMs or so, this ran off of a DSL line off of a machine in my basement. You saw it. The little, I built it myself kind of thing. And so we served up millions of free boot ROMs for etherboot. It's working great. OK, now we are going to demo. We are going to demo. Here's what happened. I kept on sort of pushing on the Pixie side. And the etherboot people sort of kept pushing on the etherboot side. And then one day, we forked because it was clear that they didn't want Pixie in etherboot, and we felt that we had to have Pixie because, like, it was everywhere. It just seemed like the thing to do. So how long did we fork? Like,
you had Pixie before you forked.
Right. We had etherboot plus pixie, but we wanted more. But it was like a couple months.
Yeah.
This might have been only a few weeks. Okay, so what happened is 3 of us went over, created gPXE.org, and started doing our evil deeds. And then the project leader for etherboot quit. And so at that point, we moved back over. And I became the project leader. Michael became the lead developer. And our partner in crime here, HPA, got his open source Pixie stack, the thing he always wanted. So we have embraced the Pixie standard. We have embraced it so much that we've added certain things.
Embrace and extend.
Embrace and extend. What is our favorite thing that we have added?
TCP?
Yes!
We like TCP.
Where's Nickel? Nickel? Stand up. Okay, come up here. Come on up. Come on up, Nickel.
Hey, Marty,
All right.
Marty, for
Yeah.
history, you should do Marcus's version first, really.
What's that? Oh, okay. Marcus, get over here. All right. Okay. This is fun. Come on. It's all right. Look, no one's going to be crazier than me. You guys are going to look normal. Okay. So Marcus put a small HTTP stack in etherboot. And it was sort of just...
It was more or less a proof of concept.
Yeah, but they can hear you. Okay. Oh, yeah, there you go.
Does this work? Okay. It was more or less a proof of concept. I figured booting over TCP and ultimately over HTTP would be a lot more useful. But working at Google, I didn't actually have enough time to fully commit to the project anymore. And that was one of the reasons why I was very happy that Marty had stepped as the project lead. And he strung on me to show up at Linux Expo and be at the booth for a while. And while I was there, he hinted at maybe this idea about HTTP booting would be really good. And since you're here anyway and you're not working today, why don't you implement it? And I remembered enough of TCP that I could implement most of it, but I didn't actually have any of my books there. So I got it to the stage that I could boot over HTTP, but I definitely still had a whole bunch of shortcomings on it. The one thing that I was very proud of is that I fitted into, I think, less than 2 kilobytes, a full TCP stack, including an HTTP client. And I think it lived like that for probably a year or so.
Oh, yeah. It looked like that for a little while.
Yeah, so people looked at it a few times and was like, well, this is really cool. But it clearly wasn't production quality at that time. And so that's when...
Did you tell them about the part where I locked your laptop to the table at Linux World Expo and refused to give you the key until it booted?
Well, I like the part better where halfway through the project I had issues with the drivers, and so supposedly there was a way to debug it in QEMU, but this was all really new, and QEMU kept crashing on it and everything. And so it finally turned out that the only person who was known to ever have seen this actually work is Michael. And he was in the UK at the time, so we called him on my cell phone, which I think usually involved running out of the conference, which didn't have reception. It's like, okay, I typed this in, it doesn't work. What do I do now? But yeah, ultimately we got it to work, and later I think this was the foundation for the new and fully implemented TCP stack that then got implemented as the Google of Code project.
All right. Okay. Enter Nickel C. Rao. We got involved with the Google Summer of Code because as a volunteer project, more hackers is usually better. And so we were really grateful to Google. We started in the 2nd year. This is now our 3rd year of participation, and we were very fortunate. Actually, Michael, you should come on over, because Michael was actually Nickel's mentor.
Our mentor. Tormentor.
Yeah, there we are. There we are. Okay.
I'm just kidding.
I
have a radio.
Oh, you already have it. Hold on a minute. Okay. So, we had IRC. Did we have IRC? Yeah, we had IRC.
back then.
And we have a lot of fun with Google Summer of Code. I got to tell you, Google Summer of Code has really changed our project, because when you got like people spread out all over the world in all these different time zones. So what was your project?
So I was helping Michael build the TCP stack that went into gPXE. So we basically had to, we used to use micro IP, right? The
UIP, yeah.
UIP.
Yeah, we'd only just started with that. So we had the UDP IP stack, which I guess you did? Yeah, you or Ken or something. People before my time had done. And then we needed TCP in order to support iSCSI, which somebody was prepared to give us money for. Which is how many features get added.
That's how they do.
Actually,
So I crowbarred UIP in there.
yeah.
And then your project was rewrite the TCP IP
To
stack.
basically keep
because
the
UIP
APIs the
sucks.
same, but rewrite what was inside, and we had to basically take the RFCs and strip apart anything that was not necessary and try to fit this this TCP stack into like a couple of kilobytes. And that was interesting. That was a very interesting.
What I really loved is you got to understand. The technical side is fun. You're just sitting there reading all these debugging commands going by, trying to figure out, arguing about, can we afford, is that worth 200 bytes? Is that worth 200 bytes? Your data your data structures, what is that? What is that field? But you also get the personal side. So we'd be like, I'd get messages from Nickel like this. I'm really sorry, but I'm stuck over at my brother's house. There are riots right now, and so I cannot leave. It was also monsoon season, so there's like waist deep water running. So if I get cut off, it's because the power has gone out again.
This was one summer. I was in Bombay. I was sitting in Bombay and doing all this, and this was when there was a bomb blast in Bombay, and basically we couldn't get from where I was to my place. So yeah, it was an interesting summer.
It was a fun summer.
But he kept hacking.
But he kept hacking. He kept hacking through floods, through riots, and the stories were really good. It's like somebody smeared something on somebody's wife's statue, and now there's a general strike.
It's almost as bad as LA.
Yeah. And so it's like you get a real global education through Google Summer of Code. Is Kat Allman here? Where's Kat? No Kat? Okay, if she sneaks in, I want to introduce her, because Krista Bona and Leslie Hawthorne and Kat Allman and the folks in the OSPO open source project office are totally awesome. We've really enjoyed working with them on Google Summer of Code. So wait a minute. I'm not done embarrassing you. Hold on one moment. So we want to thank Nickel for the first sort of extended robust version of TCP/IP, and there was some IPv6 stuff in there too. I remember.
That was actually the real goal. The real goal of the summer was to implement IPv6 support, but we only got far as we got some IPv6 support, but it wasn't.
Yeah, well, 3 months for IPv4. You know what I mean. Thank you, Nickel.
Thank you so much.
All right. So let's see. Where were you in our story?
Marty.
Yes. Oh yeah. Oh, sorry. Okay, so we forked the project. It lasted 3 months. We took over. We were the lawgivers. And HPA had been instigating for a open source TCP or open source Pixie stack, and we were like, okay, yeah, we think that's a good idea too. And so I think we should do a demo of sort of network booting using gPXE, but let's do something. You want to do the HTTP thing, Michael?
Which one?
How about LTSP over HTTP? Okay, what this demo is going to show you is network booting a workstation as an X terminal using HTTP instead of TFTP. And the reason that we did this is because, as Peter will tell you, a lot of people wanted to be able to boot using a protocol other than TFTP for various reasons. All right, what Michael's doing right now is just modifying our dhcpd.conf file so that we can choose our demo. We got like a whole bunch of demos that we can do. And so we're basically just restarting dhcpd. And what you'll see is basically this incredibly fast boot.
At the wrong KVM channel.
Oh,
so.
OK. Yeah, I think we missed the incredibly fast boot. All right, usual BIOS stuff. Now this is gPXE. It's going to do a DHCP request, and boom. If you've watched Linux boot, you know what this is. But basically, this has all been done over HTTP. Now this is a really big deal, because doing things over HTTP all of a sudden frees you from the subnet. So you should be excited and terrified at what you see here. Because imagine people being able to like stick in a USB key and hit reset and then boot their machines off of some arbitrary URL. Pretty cool idea, eh? So this is just a normal X desktop. But we wanted more. We wanted so much more. You want to do the illicit operating system over AOE? How many people know what AOE protocol is? Got any? Ah, there we go. ATA over Ethernet is this very lightweight protocol, which is basically just an Ethernet header and an ATA packet. And it's sort of subnet bound, but it's really, really efficient. What you're going to see here is something that basically we are the only thing that does it, much to the chagrin of some large multinational companies. But what we're doing now is we are loading. This machine here is our AOE target machine. So we're loading Windows XP using AOE protocol. We are literally reading the boot block off of the target machine and running the NT loader and starting up Windows. Don't worry. In a minute, we will cleanse our palette by doing the same thing with Ubuntu.
Given that we're at Google, do you want to actually be a bit more specific about how we do this?
Yeah. No, you be more specific. You're the man.
OK, so I don't think you introduced the test machine yet.
Oh, yeah. Let's introduce the test machine.
So hopefully this is not going to kill the power if I do this.
No, you got it.
Here is our test machine with no disks in. And the E1000 card flashed with gPXE and firmware. Sitting right there. So for an AOE or iSCSI boot, we do the DHCP part of boot as normal for Pixie clients. So send something out, get a reply from the DHCP server, which tells us what to boot off the network. Normally, that's going to be a file name. Now, we've already extended Pixie to the point where that file name can be a URL. So if it starts with http://, we don't do a TFTP download. We go and grab that from a web server. We also look at the root path field. And if that tells us we're doing an iSCSI or an AOE boot, we don't do any kind of file download at all. We hook int13 for the BIOS, which is the BIOS disk interrupt, dating back to, what, 1980-something?
Yeah.
1981.
1981.
The very first PC.
And the BIOS at that point thinks that there is an extra disk present. So if you use int13 to read drive hex 80, which is the first hard disk, we've intercepted that. We convert that to iSCSI calls or AOE calls going over the network. And as far as the BIOS is concerned, there's just one additional disk in the system. So this means immediately that you can fire up something like MS-DOS, which continues to use int13 all the way through because it never knew anything other than BIOS disk drivers, never had a native driver. It also means you can load anything that expects to have a disk boot sector, so something like Grub or Lilo or NT Loader. Any of that stuff will function immediately, and you'll be able to boot from a disk image as though the physical disk is attached. At some point, you have to hand over to the operating system. So when we boot up XP, int13 happens through NT Loader. NT Loader drags in the kernel, registry, any drivers it feels like, and then we get out of the way, the XP native driver for the card comes up, and there's a tiny handover table telling it what to go and boot from. And then eventually it comes up, and we will see that as far as Windows is concerned, it has one disk attached, which is there.
Oh, right-click properties on that. Yeah, and yeah. Yeah, there it is.
Not helpful.
Yep, there's our AOE disk. Now, this is kind of cool because this is how an open source project kind of works. The major corporation that's interested in AOE is called Coraid. They make most of the AOE hardware. They make these really fancy racks. And by the way, Coraid sells racks that run Plan 9. So if there are any Plan 9 folks in here, this is one of the major uses of Plan 9, Coraid's hardware. Now, there was a fellow in the Netherlands who wrote the Windows driver for AOE. Michael wrote the AOE booting support and created the mechanism for handing off between our driver and the native Windows driver. Because up until a certain point, we're doing all of the disk I/O. And then at some point or another, Windows loads its AOE driver, and it at that point has to find the right volume to mount. And how does it do that, Michael?
OK, so you're quite limited in terms of ways you can hand over to the operating system, because we're in quite uncharted territory with the bars. You've got no memory protection really set up. The only sensible thing you can do is drop a table in base memory, which is what IBM decided to do for iSCSI, and we stole that idea for AOE. So we drop a table in base memory, which Windows can scan for, and that contains basically something to identify the network card, so the MAC address or PCI bus device function, something which will tie you down and say, yes, you need to bring up this card. And another piece of information saying this is the disk you need to attach to. For AOE, that's just a 24-bit number. And that's it. That's all the information you need for AOE.
All right. OK, there's got to be one question out there. Anything. Please, ask us anything.
Question.
yes, please.
OK, so it looks like you have a great system for booting a machine using gPXE. If you have like a kind of a master-slave configuration, you have like a master serving up gPXE images. How does that scale to thousands of machines? Like, say that you just have a whole cluster, or maybe many clusters, and you want to boot them all with gPXE, and you turn them all on at once. What's going to happen to that poor head node?
OK. Actually, doing it with gPXE is going to scale a lot better than with standard Pixie, because standard Pixie uses TFTP, which is subject to the to something called the TFTP capture effect, which is TFTP is a very simple protocol. It generally uses a simple exponential backoff algorithm and a lockstep scheduling. If the TFTP server isn't very careful, and very few of them are, including the one I wrote, you are subject to the situation where the node that gets through the DIN will basically always get what it's asked for, because they will always beat the node that fell back. With TCP, you have a much better chance. The TCP backoff behavior is much better, and TCP stacks are much better tuned. So you're much more likely to actually get. Obviously, if you can't, if your links can't handle all this stuff, then yeah, you're just going to be slow. But it should be slow as opposed to falling over.
Yeah, there's also the multicast. So even standard standard Pixie supports some disgusting Frankenstein hack of multicast TFTP.
Yeah.
We support several other multicast protocols. So we support RFC compliant multicast TFTP,
Right.
unlike Pixie.
Yeah, because of course Intel had to create a whole different version of multicast TFTP than is in the RFC for multicast TFTP, and their version is particularly brain damaged. That being said, multicasting is one of those things that sound really good in theory and tends to suck in practice. First of all, it won't actually buy you that much. Because as soon as you get through the initial booting phase, you have per client specific traffic anyway, and you're back down to unicasting. As far as servicing a lot of clients from a server or a cluster of servers, I am not going to stand at a talk in this particular company and pretend I know anything about it.
But one of the cool things is it's a good question. We don't really have a few thousand servers to test it, but we would like to. And
we know people who have tried it
Yeah.
with etherboot and gPXE. So ClusterWorks built a cluster for Los Alamos National Labs, which I think was 500 node.
Yeah.
For which Eric Biederman, don't know if anybody knows him, decided that the existing multicast protocols were just not, they were too kind to your network. So he came up with this thing called SLAM. It's either simple or scalable local area multicast is what he called it. Now, about a month ago, I was working for Statoil in Norway, where they're trying to use ClusterWorks, and we hit a bit of a problem because they were using on the client side a fairly slow driver on a gigabit network. And we were getting packet loss rates of about 80%. Yeah, now I'd never previously used SLAM, so I looked at the protocol design, and it works like this. The client comes up, sends out a list of blocks it hasn't yet received for the file, which at the start of day is the entire file. The server then transmits that as fast as it possibly can onto the wire. The client picks out whichever packets it can possibly keep up with, and then sends a list saying, and I missed this 80% of them. Please resend. So this is really, really bad if your node doesn't have checksum offload, which Pixie clients don't have, and your server is a nice high-powered machine with checksum offload on the card and can stream at gigabit line rate or 10 gig line rate. And your clients really die under those circumstances. But fortunately, the protocol is so ill-defined that you can modify the client behavior to turn it into multicast TFTP.
Ta-da!
And it works.
Now, the other thing that HTTP gives you, I made a little table while we were chatting.
Yeah. Actually, for the reference, the biggest cluster I've ever heard being net booted was 16,384 nodes booted from one server.
Oh, neat.
So I was told that it took 30 minutes to boot.
It's actually not bad.
Yeah, it's given how often this cluster was rebooted, that wasn't considered a problem.
So just to give you a little bit of idea of what we did with gPXE, we implemented Pixie, and it is our goal to make gPXE work with all of the standard things Pixie works with. What are some of the standard things that Pixie works with that we have managed to be compatible with, Michael?
We've tested it with most of the NBPs that we can find on the market. So PixieLinux obviously works, because PixieLinux rocks.
It does rock.
Microsoft Remote Installation Services works, as does WDS, which is what Remote Installation Services became. There's some deployment products from people like Altiris and Ardent. They all work. There's some more obscure things like BP Batch, which works as long as you enable one tiny hack, which says, ignore the fact that it asks you to TFTP from port 4 and assume it means port 69.
Right,
but,
yeah.
We
can't get the source code to that.
There's also, I believe, one of the problems. OK, so I previously mentioned that the Pixie protocol, as defined, is actually unimplementable for several reasons. So when you implement the Pixie, you basically have to decide what part of the spec to ignore. The gPXE people have actually done a they actually let you choose at compile time what particular hacks to apply. Not all combinations necessarily work if you pull the Git tree at any one time, but at least they're officially there. The default configuration enables the use of protected mode so that the code can go into protected mode so that it doesn't have the same size limitations, which is important when you want to have all the protocols in there. That version didn't work with an old version of, I believe it was NetBSD that went into v86 mode.
Yeah, one of the BSDs decides to call the Pixie stack in v86 mode and gets really upset if you then try to switch the CPU into protected mode.
Yeah, there's also but I think they fixed that. I could be wrong.
It's basically impossible under some circumstances to write a Pixie stack that will work in v86 mode because, say you're driving an InfiniBand HCA as your boot card, that requires 8 megs of memory as scratch space for the firmware.
Yeah.
So if you're stuck to one 64K segment, you can't really service that.
Yeah.
I'm kind of wondering who can really use gPXE? If I just take an off-the-shelf motherboard with integrated Ethernet, is there a way to use it?
I am so glad you asked that. You knew, didn't you?
Okay.
Well, before we get to that.
Well, I can answer that one.
Okay, go for it.
Okay, so the problem with integrated Ethernet is that every BIOS, there isn't a standard version for integrating option ROMs into the BIOS. Fortunately, BIOS vendors are increasingly coming to terms with the fact that they have to deal with modular BIOSes, and so a lot of them now have flashing tools where you can flash a specific component to the BIOS. That being said, if you can't do that, there is Pixie chain loading.
Control plus, Control plus, Control plus. Type Control plus 3 times.
Yeah.
Thank you. All right. It's just bigger. Yeah, Pixie chain loading is where instead of, we had the Pixie model of Pixie starts up, loads a second stage bootloader or an NBP. Now, as perverted as it may seem, what if that second stage bootloader that it loads was actually gPXE? Then you wouldn't have to reflash your network card because Pixie would start up, load gPXE. We would immediately kill the old Pixie off, leaving no trace. And then you would have all of the features of gPXE.
However, even this was a little too complex for a lot of people. So we have recently, the group of us worked on this nifty little thing called gPXE-Linux, which is gPXE and PixieLinux turned into one image called gPXE-Linux.0, and it is a drop-in replacement for PixieLinux.0. The .0 is a Pixie convention for the bootstrap file. This image can do everything that PixieLinux can with one minor exception, which is the ability to chain load another NBP, and that's a bug, and we'll fix it.
Yeah.
But it can do so, once you have gone through and loaded this image, which is about 47 kilobytes over TFTP. Everything else you can do over HTTP or whatever you want.
All right. The other thing that I believe we haven't explicitly mentioned, but was a feature from pretty much day one in etherboot, is that your etherboot or gPXE image doesn't actually have to live in ROM. You can build it differently so that it looks like a bootloader or like a kernel and can be booted from a regular bootloader. You can put it on a floppy, you can put it on a hard drive, you can put it on a USB stick. There's even a feature to compile it into a DOS binary, which at some point people really liked when DOS was still popular and could just run it as a DOS program. So there are still plenty of people that use that option, and for a lot of deployments that makes perfect sense.
and you don't actually have to flash it into physical hardware.
Yeah. Also, there's one more option, which is that, let's say that you have a nifty new board with, with a gigabit or 10 gigabits interface. You can go out and buy an old, 10 or 100 megabit card with, a flash or a socket, and put gPXE on that, and use that card as nothing but a carrier for the ROM. This is actually, like in theory, you could have a dedicated board that just had a ROM socket. It's actually cheaper to buy a buy a NIC.
So gPXE, these three protocols, HTTP, iSCSI, FTP, protocols that require TCP was what drove us to embed a TCP/IP stack. Now, the current TCP/IP stack is about 4.2 kilobytes of code, which is pretty small for what it does. It handles, it's a pretty highly robust stack, and it handles quite a few situations. Let us do a demo.
Yeah.
What are you thinking, Michael?
We're going to do the Pixie knife demo.
OK, this is a really cool demo. And assuming that
we haven't checked the external connectivity.
Yeah, I'm using a wireless bridge to sort of bridge the guest network to a wired network so that we can be behind a firewall here. But I think it was working a minute ago. This is going to boot from Peter's server. Where is your server, Peter?
Oh, it's down in Santa Clara, but it's sitting in a colo. Yeah, this is all pulled over HTTP, over the internet. This is possible partly because of this interface between gPXE and PixieLinux. All of this is standard PixieLinux. I actually grabbed a friend of mine's PixieLinux setup and just put it on an HTTP server and changed the URL. But the current version of gPXE has this feature that you can embed. It would do what's called an embedded script, which is basically you can think of it as it's a compiled-in override for what the DHC server tells it. You can use it for doing static IPs, but you can also do, in this case, what I did was overrode the boot file name.
Yeah, so imagine that you're somewhere and you don't have your tools with you, but you have gPXE on a USB key or something, and you basically boot it up and there. It would have gone to local boot. You basically boot it up, and you want to drive? You want to
I'll drive.
Yeah, why don't you demo? You basically just boot it up, and you have all of the tools at your command. So this is just some arbitrary server. We test gPXE's HTTP booting all the time by just booting machines off of anywhere. Like I boot from Cambridge, England. I'm in Boston. I'll just boot off of Michael's server in Cambridge. So what we've really done here is we have virtualized booting so that you don't really think about, everything else is virtualized. The file system is virtualized. So why not virtualize everything from the first boot? And that's our concept. Pixie was stuck here at TFTP. TFTP is a really horrible protocol for getting any speed at all. Let's do TFTP. SYN.
Oh.
No.
SYN.
No, that's not TFTP.
TFTP is over UDP.
Oh, okay,
Yeah.
sorry. Okay,
Yeah.
go ahead.
Shall we do the TFTP?
Yeah,
We'll do
ahead,
it.
you guys do it. Okay,
You want to be the client?
I'll be the client.
Oh, wait, you're hiding behind
All right,
that.
I need
Okay.
to.
Marty, you're going to be the packet. You have to walk between.
I'll be bouncing. Go ahead.
Okay. RRQ. I want file boot.
Block 0.
I don't want that anymore. Error. I want boot. This file boot.
Block 0.
ACK.
Block 1.
ACK.
Block 2. Block 2.
ACK.
Block 3.
ACK.
Block 4, under length.
ACK.
That's it. There you have TFTP. OK, now, you want to do HTTP?
We'll do TCP. It's doing HTTP over. It's a little bit annoying.
All right.
All right. SYN.
SYNAC.
Window size.
Didn't see an ACK. I'm dropping your connection.
SYN.
SYNAC.
Window.
Data, 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 data,
Data, data, data.
ACK.
data, 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 done.
ACK. Pin.
There you go. So the idea of HTTP is not just that it is a reliable protocol, but also that it's windowed. So, you know, I can sit here and go, data, 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 and he can just act as he goes on. It's the difference between X modem and Z modem. And so that is one of the reasons why you like it. The other reason is that all of the layer 3 appliances, all the load balancers, all of those cool boxes that people have to make
Layer 4.
Pardon?
That's layer 4. Layer 3 is IP.
Right.
Yeah.
Oh, OK, sorry. Layer 4. Bleh. All right. All the layer 4 stuff can help you. So essentially, it can look and it can load balance. It can prioritize your traffic. It can do all the things that you want help with. TFTP is often blocked at switches and routers, but HTTP.
Yeah. In fact, one of the main source of requests for, I mean, I've been getting this for years that Pixie Linux users want HTTP. A lot of them, it isn't actually due to any of the problems with TFTP. It's actually due to the fact that, well, they know how to do customizations in Apache.
Yes.
You have this huge infrastructure for delivering HTTP content. And you know, they want to be able to generate configuration files dynamically and do all this kind of stuff. And like, they already know how to do it on HTTP. They don't want to have to deal with a completely different infrastructure for TFTP.
A machine wakes up. It does its DHCP conversation. And during that DHCP conversation, it informs the server of some things. Then it has an HTTP conversation. During that conversation, it talks not to a static file. It talks to a CGI. In talking to that CGI, it specifies the kernel and the modules and everything that it needs, so it does not have to load down the world. It only loads down, it tells the CGI, give me the RTL8139 driver. Give me the particular USB driver.
Do you want to see this happening?
Yeah, let's see that happening.
You had a question?
Yeah, is there any kind of authentication on this? Or with like the DNS spoofing, could somebody just take over your boot?
Oh, yeah.
Yep.
Oh, yeah.
So there is authentication or there's not?
No. No. This is...
No, we have, it's something that is going to happen at some point. We have a TLS layer, so we can do SSL v3 and TLS v1. At the moment, it's an incomplete implementation. It won't actually verify the server certificate, but it will convince the server that it can speak HTTPS.
But in answer to the question, right now, what we have is danger, Will Robinson. But we know what we don't have. We're not crazy. We're just basically creating capability and then creating more capability. So as people ask for stuff, and particularly where clients come to us, you might say, well, how do you open source guys actually like do all this stuff? Well, quite often, now that gPXE's grown up and does all this stuff, people contact us and they say, well, that's all great, but can you make it do this? And we'll say, sure, but that's going to be a lot of work. We'll have to get some funding for that. And so that's kind of how we do it. The HTTP support is pretty good and pretty robust. The HTTPS support needs some work.
Yeah, it was a proof of concept demo for an OEM that shall remain unnamed.
Yes.
They
You
wanted-
want to explain this? Okay.
Well, this bit here.
Yeah.
Yeah, so this is what you were talking about a couple of minutes ago, where, has anybody got a laser pointer? Okay, I'll just point with the finger. You see the line saying booted from? That's basically what the DHCP server handed out, except that in the DHCP config file, it said that. So we have, in particular, this bit here, which is basically variable expansion. So you see UUID equals and then expanded variable, which on the client side,
Have some fun. Red button.
we're here on the client side. So that's where we had $open brace UUID. That's been expanded by gPXE to the UUID as ripped out from SMBIOS, and ditto for the MAC address there. Don't ask me why there's an extra colon. I'm going to debug that this afternoon. So that went off to this PHP script, which then generates this. Now, this example is actually just hard-coded, but the principle is you could stick any information you want about the booting client in the DHCP request. The web server running some kind of CGI can then generate a boot script for you saying, yeah, you've got to load a kernel from here, user space, initial RAM disk components, and a few kernel modules, and then boot the whole set.
Yeah.
And when it comes up, those modules will be present in the file system at that point.
In fact, it's even it's also possible. Since Pixie Linux and gPXE now work, you can actually do a lot of you can do the equivalent client side as well. There is an API in the SYSLINUX distribution that to actually go to take to not just to probe your hardware, to request things from the server, and make and make this all automatic. And it will stitch together an init-ramfs for you on the fly and boot it.
Can you bring up the Ubuntu over iSCSI demo?
Yeah, if you want. By the way, GDB works.
Oh, you got GDB?
I had the wrong
Okay,
tray.
all right. Let's do the G. How many people here use GDB? Cool. All right. One of our summer of code students this year, Stefan Hajnowski, his project was GDB debugging for gPXE, because sometimes you just want to like interrupt it and get in with GDB and like take a look around, while gPXE is running. So Stefan was really amazing. It's like Google Summer of Code started like on a Monday, and like on Wednesday, his journal entry was implemented initial GDB support with serial mode. And like, we had expected that to be done by like 6 weeks, like midterm. And he didn't slow down. He went on and implemented GDB over UDP and a whole bunch of other stuff. All right, so what are we going to see?
Just give me a sec.
All right.
OK, so client is actually displaying just here at the moment. I don't think we can get split screens on the projector. So this is not going to be doing much, but this is showing you gPXE at boot time. So we haven't loaded the OS yet. We just dropped into the gPXE shell. My laptop is running GDB, and I'm connecting via serial cable to here. So I'm going to start the client listening for a connection, and then drop in. And it's worked. Oh, thank God for that.
Yeah, sweet.
We had issues with this earlier. OK, so we have no operating system running, but we do have a GDB stub living in there. It's about 1 or 2K, I think, when it's running over the serial port. And this means that we can do everything like set breakpoints, run it through, drops us in there. You can single step through the code. It's quite slow when you run over serial. Running over UDP, which we also support, is faster. But since what I'm going to show you is debugging the network card driver, that's not going to work if we try doing it. If you've got 2 network cards in there, you can do that, because our stack supports multiple cards and IP routing and so on. So that's viable. OK, so this is now stepped through to the point where we're in the driver's poll routine. I'm just going to kill off the breakpoint I've got. And say we have a bug which hits received packets and only happens at a certain length. So
Wait,
Go
that's
down
my-
to the part of poll.
that's
Yeah,
my code.
This is your code.
That's
yeah.
my code.
Oh,
So let's drop down to there and set a breakpoint at that point.
Claire needs to be debugged.
So run until we hit it.
Yeah,
So at this point in the code, we can try inspecting variables. We find that quite a few of them are optimized out because we've run with incredibly aggressive optimization settings.
in order to get the ROM size, keep the ROM size
Yeah.
as low as
Oh,
possible.
our aggressive optimization settings are sufficiently aggressive that GCC decided at one point that our mem copy routine didn't exist. It could be optimized away entirely. Don't turn on f-strict aliasing unless you've thought through the consequences. So yeah, say we had a network problem which materializes halfway through an operating system boot and happens, we know when packets are over a certain length. So I could say make this breakpoint conditional on the packet length being over a certain size. And then just run this thing through. And the client at this point, I don't know if you can see the screen, but that's dropped back to the prompt. So there's not a lot happening, but this is still running as normal. If I now set this through to go and actually boot off something, this is where...
I think one of your commands didn't work. Try.
Oh, yeah, DHCP net 0, I think. Yeah, that's it.
Yeah, so I can grab an IP address via DHCP. We haven't got into the debugger
There we go.
because
Yep.
we haven't hit a packet over 512 bytes. If we quickly reconfigure this, this is where it gets interesting.
Turn it around for you.
Deep
Quickly turn it
magic.
In fact, that will do. I think.
Okay.
Let's switch that. So I'm going to switch this back to doing something like an iSCSI boot, where it's definitely going to end up doing large packet sizes. And let's hit the client again.
This turned out to
Okay.
be incredibly useful for debugging some stuff. Before this, we had to debug with printfs and just pretty primitive debugging. But by getting this, and this was a Summer of Code project. We put it out there on our list of Summer of Code projects. Somebody volunteered for it, and we got 4 really great students this year. And I'll tell you about some of the other things that they provided.
OK, so I've let this go through and start its boot as normal. It's going to attempt an iSCSI boot of Windows Server 2003. But it will run very, very slowly. But what should happen is the first time we get a proper TCP data packet, one that's over 512 bytes, is at a breakpoint.
It's at a breakpoint.
And it worked.
Yes.
We've only tested this once before, by the way.
Oh, yeah.
So it's quite handy to be able to go in and just dump stuff. So for example, let's take a look and see what the length of this packet actually was. 630 bytes.
Okay.
And if on the right-hand side I scroll down just a little bit further, you can work out from there where the packet's actually going to be. So I can just, for example, dump this out by doing
Sweet.
and there's the packet. So this is the packet being read out of memory on the client system. And it looks as though GDB's fallen over.
Right.
No, it's just going slowly.
But you can see that the MAC address.
Yeah, you can see that the first 6 bytes are correct because that is the MAC address of this card.
That's the MAC address of the E1000 card.
So it's quite handy to be able to dive in and do some debugging that's a little bit more sophisticated than printf. So we're really grateful to Google Summer of Code for that.
We're really good. So that was Stefan's project. We had 3 other projects. One was Michael Decker, who did network drivers. First he did the EE Pro 100 driver. He ported that into the native API. Then we had Daniel Verkamp, who implemented the COM32 interface of SYSLINUX.
This is basically a way to run. This is a more deep integration of gPXE and Pixie Linux than what we have done in the past. This is actually running SYSLINUX modules directly on top of gPXE. It's a bit experimental and probably will be that way for a while, but it's kind of the long-term future of this project.
And the final student we had was Balaji Rao, no relation. But his project was to add USB support to gPXE. So with his code, you can plug a USB to Ethernet adapter into a machine and run gPXE, and gPXE will run over USB adapters. So we are really thrilled. We've done really well with Google Summer of Code, and it's been a great blessing for us. I want to get into iSCSI. We got like about 20 minutes left.
Oh, did we go to 4? Does it go to 4?
Yep.
Okay, sorry.
Yep. We took the large economy size talk. You know. All right, iSCSI. How many people are familiar with iSCSI? iSCSI people? All right, think SCSI over TCP/IP. Okay, with all that portends. It's routable. It's it's windowed. It's fast. It is RFC'd.
It's hideously complicated.
It's hideously complicated. It's that.
And we
big.
implemented it in 4K.
And we implemented it in 4K. Yes, it's amazing what you can do when you try.
That's about 1 byte for every page of the iSCSI specification.
Oh, it's about a byte for every 3 pages. Let's be fair. Yeah. All right. What iSCSI allows you to do is to treat a remote disk as a local disk. So why does this become interesting? Because some operating systems stubbornly refuse to be network booted. They just don't want to do it. For some reason, that one, for example. So essentially, what we have done is we have implemented a way to boot operating systems off of disks that aren't physically attached to them. Now, modern operating systems actually allow you to install the operating system onto an iSCSI target. An iSCSI target, think of it as like a large server array with lots and lots of disks on it. And your client, what is it, 3260 port number?
Yeah.
OK. TCP port number 3260 is the iSCSI port. And we can network boot various operating systems. Have we network booted we should network boot a Linux. I don't want people to think that we sit around all day long booting Windows, but we get lots of requests for booting Windows, so we can do that too. But
well, the thing is, there are so many other ways you can boot Linux.
Yeah, there are so many other ways that you can boot Linux that it's kind of like not as exciting to people because everybody does that. But we're a bootloader. We boot what we are given. If we didn't, we wouldn't be a bootloader. So this is where iSCSI becomes a really interesting protocol.
Did you want Fedora or something?
Let's do the Ubuntu. They use Ubuntu here, or Ubuntu. So let's do the Ubuntu iSCSI. But this is where open source projects sort of like where you find out whether you really believe in what you're doing, because when we first implemented iSCSI booting support, Microsoft sent lawyers after us because they claimed that the low memory table that we were using, something called the IBFT, iSCSI boot firmware table. It's the little table in memory where you dump the information about where you're booting, where the native Windows driver is supposed to continue the boot from when you hand off. They actually claimed that that was proprietary and that we were not allowed to implement that. As it turned out, IBM was their partner in this, and IBM published their specification. And so eventually, after consultation with the Software Freedom Law Center, we were able to implement our code based on the IBM specification, which is just slightly more complete than the Microsoft specification. And life was good again. But this is the adventures that you have in open source, where you want to do something because you can. You want to do something that seems perfectly normal and natural. And sometimes you have to look at things that seem like they're really out of band to the problem in order to get the problem right. So, oh, you did it.
Yeah.
Oh, well, there we are. OK. Same process here. Instead of loading the NT loader off of the boot block, we loaded grub off the boot block. Grub had the illusion that its int13 calls were being serviced by some disk, but it was us. And then about halfway through the booting process, the native Linux driver did its thing, and blah, blah, blah. You get the idea. All right. Any questions? Wow, we must be good. Yeah. The question was, do we have images for memory sticks? Do we have memories for ISOs? Or do we have images for ISOs? Do we have memories for floppy disks? Do we have images for you just about name it? Why, yes, we do. So if you're using, hey, Michael, do a QEMU boot just to show them that we can do it. A lot of people are into these virtual machines. What we're into, our latest sort of kick is booting virtual machines from virtual disks. So firing up QEMU and booting it from a server in England, just because you can. What this does is it not only virtualizes the machine and whatever storage it is, but it virtualizes the boot source. So you can imagine, like, booting from someplace far away.
Whose phone? Not mine. Mine's not GSM.
Oh, OK.
That was a GSM noise.
Yeah, GSM noise. Sorry about that. OK, tell them what you're doing, Michael.
Keep talking, because my laptop crashed 2 minutes ago and I had to reboot it.
Oh, OK. What Michael's going to do is to create a disk image for QEMU. So essentially what QEMU will think is, it will think it's booting off of a floppy. But the floppy will actually be a gPXE, what we call a P disk, or a padded disk image. QEMU wants 1.4 megabyte images. It just does. You can't give it a 40K floppy image or it gets upset with you. And what it's going to do is essentially boot off of that, start up gPXE, and presumably boot off of something interesting.
I'm going to boot this one here, unless you've got any better ideas.
Go for it. Is that machine up? Do we know?
That's my laptop.
Oh, OK. That machine is up.
Keep talking.
Oh, OK. Sorry.
You should have given me more warning you wanted me to do this.
OK. Let me tell you about some of the other things that we can do in terms of booting. We work with Box. We work with QEMU. What's this KVM thing, Peter?
KVM?
Yeah.
It's a hardware accelerated version of QEMU. It's probably the easiest way to describe it.
OK. So we work with a whole bunch of emulators. We work with VMware. So you can test booting various operating systems in VMware using gPXE. And it's actually quite cute. You want me to do one of the... Oh, OK.
Hey, it worked.
There we go. So what is it that we are booting?
I'll tell you if it works. Yes, it does work. It's just the same demo you saw earlier with an HTTP boot, but this time done in VM. We do lots of the development in VMs because before we had GDB, it was impossible to actually debug on real hardware in any meaningful way other than using printf. Whereas in a VM, you can at least single-step through things, particularly in Box. Box is a great VM for debugging because you can single-step the CPU through any kind of contortion you want. So if, for example, you're trying to debug your mode transition code going from real to protected mode, you can do that in Box. You can single-step through it and see everything that's happening. Whereas you try doing that any other way, and you're stuck.
This is really cool because virtual machines are so ubiquitous now that it seems like having virtual boot sources makes a great amount of sense. So it's almost time to wrap up. And with the last 10 minutes, all questions are fair game, if anything comes to mind. And while you're thinking about it, I'll sort of give you a summary of the etherboot project. Let's fire up the etherboot project webpage, because we didn't make any PowerPoint slides or impress slides. This project has been going on for 13 years, mostly because some of us think that network booting is about the coolest thing we ever saw. And so we keep trying to find new and cool ways to do it. If you think of anything that we aren't doing that you think would be cool to see, do let us know. Because, these long winter nights, we find ourselves desiring to hack on kind of neat and weird stuff. Thank you. we boot, let's go to the how-to guides. This is one of my favorite parts of the project. As project leader, one of the things I do a lot is to try and get more people involved in etherboot. And one of the ways to do that is to realize that not everybody is going to be a world-class kernel or hardware hacker. But a lot of people come in who have figured out neat applications of the technology. We turned our entire web page into a wiki. And what we do is if people come on and they have a problem and we help them, we'll ask them if they wouldn't mind creating a page or editing a page on the wiki, or if something didn't seem like it was clear and we had to, we work with them for like an hour or two helping them debug something, we just ask them to like add something to the wiki, and it works really well. We've gotten some really neat things like installing, installing Windows Server 2008. Hey, why don't we boot one of those? We got a few minutes. You want to boot? We got Vista and Windows Server 2008 to boot under gPXE, but they're such pigs. They load so slowly that they make a really kind of an annoyingly slow demo, even on a gigabit card. But we can show them to you anyway, just so you can see what they do. Any questions about the project or network booting in general? Gee, it must be good. This is scary. Michael, anything to add?
No, not really. I'm kind of curious to know what uses, if any, people are putting gPXE to here. Given that we've had patches contributed, I'm assuming you're actually using it.
Well, they could tell us, but then they'd have to kill us. Yeah, where's Andrew? Andrew. Yeah, so Andrew, we were like hanging out on IRC one day, and like we started getting these patches from like Andrew Schran. We started getting these patches from Andrew Schran, and so like who's this Andrew Schran guy? And he just kept sending them, and they were it was cool code, it was like, yeah, that seems like a useful thing, and so we got to talking, and I found out he was an intern here, and he's the one who made most of the arrangements to set this talk up. So I want to thank Andrew Schran for like going through the maze of like forms and websites and things. Like this table required a thing, and like getting every little piece of everything required stuff, and we're really grateful for you for doing that. Nickel, we want to thank you for TCP/IP 2 years ago, and for more Michael magic. We had a saying where we just say MMM because Michael writes code. When you watch Michael write code online, it's weird because it comes out looking like it's done, even when it's not. It's just like comes out perfectly formatted and logical. I want to thank Marcus Gutschka for like not only like letting me like crash at your place, but also for starting the etherboot project. I want to thank Peter Anvin for Pixie Linux and for helping us to see the one true way of Git. As we were leaving CVS, we had momentary illusions that we should just move it all into SVN. And Peter said, why would you do that? And so we ended up in Git, and it's been great. It took a little while to get up to speed. Were you there the first year we were using Git?
No, I was there when Git.
Oh, okay. The first year of Git was a little weird, a bunch of CVS newbie, CVS, but Peter was there and he helped us. And of course, I want to thank Michael Brown, because Michael Brown is an amazing hacker. And I often tell people that being in the etherboot project or being in a very small open source project, you're kind of looking at the core of the etherboot project, and the founder, 13 years ago. It's a lot like being in a rock and roll band. It's kind of like if any of us isn't online, or if any of us isn't there, or if any of us are bummed out because something's not going right, you feel it in the project. And that also works the other way. When we're all hacking together, when we're all on the channel, you've been there, and everybody is like sort of like it's like 2 a.m. and we're like debugging something and we finally get it to work, it's such a rush. So I just want you to know, I'm kind of like the lead singer. I'm like the front man. But I know that we have the best guitarist in the world, and I know that this guy is scary. Yes, I know. There's nothing scarier than having your code go up on a large screen, with HPA, having your Ethernet drivers, up on the screen. But thank you all for coming. We really enjoyed being here, and etherboot.org, ramomatic.net, and we ain't done yet.